Okay, welcome everyone to the Condensed Matter seminar. We're happy to have with us Roopali Kukreja from UC Davis. Roopali is an expert in magnetic and charge dynamics in interesting and complex oxide materials. She got her PhD from Stanford University, working in the magnetization and dynamics group, doing some really interesting studies using X-rays to study ultra-fast lattice and electronic responses in materials that were excited by lasers. Then she went on to a postdoc at UC San Diego, working with Oleg Shpirko, continuing some really nice X-ray studies of materials exhibiting inhomogeneities and kind of long-scale dynamics around phase transitions. And then since then, she's moved on to the material science engineering department at UC Davis, where she's really pushing using time-resolved X-rays to investigate magnetic dynamics and charge dynamics in these complex oxide heterostructures. So Roopali, thanks for presenting the seminar today.
Sure. Thank you. Thank you for the introduction, and thank you for giving me a chance to present some of our recent work, which I've been doing at UC Davis on this complex oxides and magnetic materials. So these systems are sort of the primary research focus of our group, and they're very interesting because of their complex degrees of freedom, interaction between spin, charge, and orbital orders. So my group looks at a variety of complex oxides, and we'll talk about some of those today. And then we also look at magnetic materials, especially trying to control spin dynamics using ultra-fast lasers. I won't talk about that work too much today because it's still in sort of a process of publication. And then we utilize quite a bit of advanced X-ray characterization techniques. So we go to national user labs and do coherent X-ray scattering and different techniques to sort of look at these materials, both at nanoscale and looking at sort of fundamental timescales associated with dynamics in these systems. And as I said, these systems are very interesting because you can actually utilize any of these sort of 4 degrees of freedom, orbital, lattice, spin, or charge, to manipulate physical properties in these systems. And you can do that using optical pulses, currents, heat, or heteroepitaxy. And the two methods I'm going to talk about is sort of heteroepitaxy, how we can use that to control phase transitions in the system, and then how things respond as a function of temperature today. And there are varieties of examples as to sort of talking about why we need to image these systems. And one of the most commonly studied complex oxides, vanadium oxide, which goes through a metal to insulator transition as you apply either heat it up or apply electric field. And you can see here in this sort of study that the transition starts with the nucleation of a metallic domain, which then inhomogeneously sort of continues through the insulating phase, and the transition switches over. And even in materials like strontium cobalt oxide, you can actually use an AFM conducting tip to cause transformation between sort of 2 different crystal structure phases. And some of these transitions you can actually cause at very, very fast timescales, which is interesting avenue for devices moving away from sort of traditional way of controlling the material, but taking and utilizing lasers to control these systems. So here you can actually change strain and lead titanate at the timescales of picoseconds and transform the crystal structure from sort of more tetragonal towards cubic. So today we'll focus more on sort of nanoscale imaging and fluctuations compared to talking more about the ultra-fast timescales, but hopefully in future we can discuss that too. So the key sort of questions in this field are sort of, when you apply all these triggers, what are the length scales at which materials start to change? Which length scales do the material respond? And then for these dynamical applications, what are the time scales involved? And what factors determine these length scales and time scales in the material? And the way we study that is utilizing synchrotron light sources. So this is an image of Stanford synchrotron radiation light source, where we have done some of our X-ray imaging work. And the advantage of going to these sources is, one, you get billion times higher X-ray intensity than you can get in an X-ray source in the lab. And it gives, because you're using X-rays, you get spatial resolution. So you can look at the atoms or any sort of orbital charge ordering which you want to study. It also, because X-rays generated in these sources have a pulse width of about 50 or so picoseconds, it gives you temporal resolution to study these systems. And then some other advantages are you can be element specific, you can have chemical sensitivity based on which X-rays you are tuning to, which energy of X-rays you are using. And predominantly for the sort of the experiments I'm talking about today, you can get coherent X-rays at these sources. For a lab source, if you wanted to get coherent X-rays and putting a pinhole to get that you would pretty much be down to like no to zero flux for your experiment. And to get to these nanometer length scales to study these materials and study dynamics in this material, this becomes a critical component, and that's something we can get at these radiation light sources. Okay, so our group has been doing quite a bit of work in different types of materials, looking at phase separation and cobaltides, exciting, looking at photorestriction and ferroelectric materials, domain fluctuations in ferroelectric materials, and controlling metal to insulator transition in magnetite and neodymium nickelates using ultrafast lasers. And then on the other hand, specifically looking at magnetic materials or heterostructures, which are interesting for spintronics application, where you have multiple stacks of, let's say, cobalt, copper, different magnetic domains. How do they switch when you actually pass a current through? How does the magnetization go from this sort of up to down state as a function of spin currents or as you're doing ultrafast laser excitation? And there's a variety of techniques which we have developed and have used to sort of do these measurements: time resolved X-ray diffraction, nanodiffraction, and coherent scattering. So today, I won't go into details of all of this. We'll talk mostly about complex oxides, and we'll focus on nanodiffraction and coherent scattering. So I've divided my talk in two parts. So the first part, we're talking about cobaltite heterostructures. And these heterostructures have sort of become very interesting, cobaltite especially, because you can move the oxygen ion in this material in and out as a function of different triggers. And that's interesting for sort of fuel cells applications, solid oxide cells, and also recently for neuromorphic computing. So traditionally, when you have a perovskite system, ABO3, people usually dope it with cations, A or B, and that gives us a variety of interesting magnetic or electronic properties. But in the last decade or so, people have been really interested in actually changing the anion, moving the oxygen anion, because that has interesting applications for fuel cells. So you can control the oxygen ion content with a variety of methods. Oxygen annealing is one example, where if you start with, let's say, a brownmillerite phase, and then anneal an oxygen, and this is the phase, and I'll talk about what brownmillerite actually means. But for now, it's an oxygen deficient phase, has more of an oxygen vacancies, which get ordered in the system. And as you anneal it more and more, you can, in oxygen, you can actually change to the perovskite phase. Now, that's not a method you can sort of use for device applications. So people have actually fabricated electrochemical cells or ionic gel gating cells where they actually apply a voltage and the oxygen ion moves in and out of the structure. And as the oxygen ion moves from brownmillerite, people have sort of tracked the transfer to the perovskite phase as well. But even though different methods have been sort of developed to look at it, there are still a few key questions. One is, what are the sort of timescales at which this oxygen ion moves? And second is the phase transformation between these phases as the oxygen ion is moving in and out homogeneous, or it's very inhomogeneous. And if it's inhomogeneous, how does the morphology looks like, or how does the sample sort of domain structure look like? And what are the critical length scales? And what factors define those critical length scales? And so our collaborators recently looked at lanthanum strontium cobaltite, especially where perovskite is the ground state. So these examples are where strontium cobalt oxide, the brownmillerite, is the ground state. Using perovskite as a ground state is much more interesting because as a choice of substrate, you can actually control the strain. So you can control the perovskite phase much more, tune it much more nicely compared to a brownmillerite phase. So this is LSCO, which was studied, which our collaborators sort of started fabricating very nice thin films of it for different composition. And this material is interesting because as a function of composition, it actually shows a metal to insulator transition, where in this part for the lower compositions of strontium, it's actually insulating. It has spin, it acts like a spin glass where you have certain ferromagnetic regions in like sort of a insulating matrix. And as you dope more and more, these ferromagnetic islands grow and the material becomes completely ferromagnetic, and those ferromagnetic channels are magnetic and metallic, so the material becomes metallic. And then so at this sort of 0.18 composition, you get to this metallic ferromagnetic phase. So that's where we were. We used composition of 0.3, where the system was deep in this metallic ferromagnetic phase. So at that point, when you take the system and you start to heterostructure it with different oxygen gather layers. So you can, if you grow it on LSAT, it's a very nice perovskite crystal structure. And then if you start to add gather layers on top, like gadolinium, neodymium, or aluminum, any such material which actually likes to take oxygen and has oxide, at that point, that heterostructure would sort of start to change into brownmillerite. So the oxygen from the lanthanum strontium cobalt oxide would move towards gadolinium. Gadolinium would get oxidized, and you will sort of get a signature of brownmillerite phase. So now talking about this oxygen deficient brownmillerite phase, it's essentially an ordered phase where as you create more and more oxygen vacancies, like you're moving oxygen ions in the system, and as you move more and more oxygen ions out of the system, you'll create oxygen vacancies, and these oxygen vacancies actually get ordered. So you have the usual octahedral, which is present in perovskite. Then the oxygen vacancies result in a tetrahedral layer, and these vacancies are actually ordered along 110 channel, okay? So they have a very specific orientation. So that orientation means that the unit cell of brownmillerite is actually 45 degrees rotated compared to this green perovskite structure. And why I'm talking about this 45 degrees rotation will actually be important as we get to end of sort of this section of the talk. And so you get this octahedral, tetrahedral layering, and that is what is the brownmillerite structure for this material. And you can control this phase transition, how much oxygen vacancies you remove, depending upon that, you can sort of control this transition, and that is as a function of gadolinium thickness. So this is an X-ray diffraction study done at SSRL, where they looked at gadolinium half, gadolinium 3, and just an as-grown system. And you can start to see that for gadolinium 3, because you're sort of quadrupling your unit cell, you start to see half-order brownmillerite peaks present in the structure. And if I zoom in to this particular Bragg peak, you can even see for gadolinium half, the system is actually different. So as you start with an as-grown material, you get the 002 crystal back peak. And then as you start to add gadolinium in the material, let's say half, you start to create oxygen vacancies. At that stage, because you're creating oxygen vacancies, your lattice would expand due to the repulsion between cations. And then so the structure actually shifts to a lower theta. And then as you increase the thickness further, now you actually move away from perovskite and start to get this brownmillerite-like phase. So this is actually a peak which belongs to brownmillerite structure. Okay, and you can image it using TEM too. You can image the cross-section of these materials using scanning, tunneling, electron microscopy, and which shows the presence of both perovskite and the brownmillerite phase. So here, if you look at sort of the red cube here, red box here, you have a very nice contrast and oscillations. So that's the perovskite structure. And then if you look at sort of the white and the blue, you get these especially the blue, you sort of get these quadrupling sort of structure, and that sort of denotes that you're converting into the brownmillerite phase. So you can look at the cross-section using this technique, but to try to look at it in sort of a lateral manner, how exactly this brownmillerite is forming, that's not very easy to do with TEM studies. In addition, this material is extremely sensitive to the oxygen ion, as we talked about. So there has been sort of question raised when you do TEM sample prep, at that point, do you add more oxygen vacancies in this material? So that leads to the brownmillerite transformation, or can actually affect this sort of distribution we are seeing here. So to sort of answer those questions, we utilize a technique called X-ray nanodiffraction, where we can look at as-grown samples or as deposited samples without doing any sample prep whatsoever. So these studies were done at Argonne National Lab at Advanced Photon Source at Sector 26. And the idea behind X-ray nanodiffraction is you do X-ray diffraction like we're used to in a lab source, except the one key difference is you use a zone plate. So this zone plate is sort of a focusing optics for X-rays, and it focuses X-rays down to about 25 nanometer spot size. So that's a very small spot size, which you can then scan over your sample and collect nanoscale information. And you don't need any sort of sample preparation. Because you have X-rays which are at 10 keV, they can penetrate over as many sort of capping layers you have. Remember, this material has gadolinium and gold. So for electron penetration depths, it's challenging, but for X-ray penetration depths, that's totally fine to sort of look at this film, which is buried in sort of these capping layers. Okay, so this is the image of the chamber inside, and this is where the sample is mounted, and the X-rays come in from here, and then you have detector on this side, right here. Okay, and before going into sort of the data we obtained, I wanted to briefly talk a little bit more about X-ray nanodiffraction technique. So the way it works is you incident the X-ray beam about 200 micron in size on the zone plate. That results in diffraction from the zone plate, which focuses down to 25 nanometers. But because our zone plate has this sort of structure, which is there is a center block which blocks the 0th order, and then you have these alternating gold and silicon nitride sort of rings, which cause the diffraction. The beam hits the sample here, and as it moves forward to a detector, which let's say is placed here, it would again take the shape of this imaging optics. So instead of looking like how we usually see a Bragg peak, a very nice Gaussian, your Bragg peak would actually look like this. And this is purely because you have an imaging optics in the X-ray beam, which looks like that. Okay, so image your zone plate and Bragg peak on top of each other. And then let's say this is where my Bragg peak is, this red. As it moves around, like here, I can then estimate how much is the strain in the sample as the Bragg peak is moving around as I'm scanning. Okay, so as you scan across 25 nanometers, you can sort of track how the bragg peak is moving across, and you can calculate the strain in your material. And in additional, if you have, let's say, two different crystal structures, which will diffract in two different Q space. So if you have zone plate, your sample with multiple crystal structures, so let's say you have one bragg peak, a second bragg peak, that would show up on the detector at a different location. So you'll have a perovskite peak right here, and you have like the brownmillerite peak, which will show up at a different Q location altogether. So at the same time in a sample, you can map exactly how much brownmillerite is present and how much perovskite is present. And once again, the shape is not because of anything to do with the samples, it's purely because of focusing optics. Okay, so now that we have that set up, we can now scan our samples and start to look at it. So we first looked at gadolinium half nanometer. And for gadolinium half nanometer, the intensity of this perovskite peak is orange and yellow, which is plotted here. And we sort of start to see some spots where we actually start to see intensity from brownmillerite phase. And then if we integrate over these brownmillerite spots and plot that intensity, it's pretty much the opposite contrast. Wherever we are seeing perovskite deficiency, we are starting to see blobs of brownmillerite phase appearing. Okay, so that's gadolinium half nanometer sample. We can change the gadolinium thickness and measure a different sample. And this is the gadolinium 3 nanometer sample measured in exactly the same manner. So here we actually start to see formation of some interesting sort of filaments in the material and very strong conversion to the brownmillerite phase. So again, you have the perovskite nice peak, giving you this yellow sort of white contrast in these regions. And there is some brownmillerite present in this region. And then if you look at these dark regions, that's where you see intense sort of brownmillerite peaks. And if you integrate that over, you can start to see the reversal of the contrast. So indeed, as you move to the gadolinium 3 nanometers, instead of having sort of this distribution like blobs, you actually start to move towards formation of filaments in the system. So that's one key takeaway. The second is, no matter where we scan the sample, we always saw sort of, if this is a perovskite region, we always see intensity from the brownmillerite. And if this is a brownmillerite region, we still see some faint perovskite intensity. So you're not just seeing this phase separation laterally, there is actually a phase separation across vertically in the thin film in here. So what we think is happening is that because you have gadolinium on top, probably the top entire layer is brownmillerite. And that's why we always see sort of this brownmillerite peak everywhere. But then the rest is laterally phase separated. And then the bottom layer probably is pinned, the perovskite is pinned by the substrate. And that's why we always sort of see a very faint perovskite intensity, even where we have such strong brownmillerite intensity coming in. So and because we're doing it in X-ray diffraction, so we're not sort of, we're not sensitive to the depth sensitivity, but that's where we think what is happening as of yet. But we still have to take the sample, cut like a cross section, and then look at the top and the bottom surface with TM to sort of confirm that.
Can I ask a quick question?
Sure.
I guess I don't know so much about film preparation, but how much control do you actually have over the thickness of the gadolinium or the uniformity of the thickness of the gadolinium layer? Do you know it's exactly 3 nanometers everywhere?
Right. So that's actually a very good question, and it's a question which we spend some time sort of figuring it out. So the thickness is we have quite a bit of control on the thickness. So 3 nanometer is pretty accurate, plus minus like 0.1, 0.2 nanometers. And we can measure that after we have grown this films using X-ray reflectivity. The surface roughness, on the other hand, when we grow thicker films, then our surface roughness is pretty good. But in this case, what we are not sure about is as gadolinium gets oxidized, because that's what's happening as we have the sample, is there sort of a distribution between gadolinium and gadolinium oxide across the gadolinium layer. And that we are not sure of yet. So at least if I just grew gadolinium without the LSCO, we know that that layer is homogeneous and smooth and it's fine. But when we grow on top of LSCO, it converts into gadolinium oxide, and that distribution between gadolinium and gadolinium oxide, I cannot comment on that yet. We tried to apply for like a beam time proposal to do this, to see the oxidation of gadolinium. Hopefully we'll get beam time soon to sort of see that there. It's not that easy to image. Yeah.
So that would be like a X-ray absorption spectroscopy experiment or something.
Yeah, so you'll be doing something like soft X-ray absorption spectroscopy, but then you will also have to scan your sample to see if there is sort of separation between gadolinium and gadolinium oxide. Yeah.
My second quick question is, I guess if you have questions about the layer, the dependence along the z-axis, I guess, is it possible to just do, you maybe don't even have to do a nanodiffraction experiment, but go to below the total external reflection angle for your film to see something like a reflectometry experiment? And if there's a Bragg peak that you can access at those small angles, you might be able to distinguish if you have these two phases at the surface.
Right. So the point is, it's hard to get to like a Bragg peak at lower angles. So if I go back to sort of the XRD, this is one, and this is about like 18 degrees or so.
It can actually be a high angle Bragg peak. You just need a low angle of incidence.
Right. So you're saying grazing incidence, extra diffraction sort of to do that. Yeah, we haven't tried that. So that is something we can try. What we have sort of looked at is our collaborators have done neutron diffraction with depth sensitivity. And while that is, they've done it for magnetic systems. So for magnetism, they can actually see that the bottom layer is fairly magnetic while the top layers are not, which is consistent with the fact that LSCO perovskite is magnetic, but the brownmillerite is not magnetic. Yeah.
Oh, thanks.
Yeah, okay. So then from these filaments, we can actually zoom into, let's say, a smaller section, and then start to look at what's happening at these regions. And we start to see some very complex sort of distribution of brownmillerite and perovskite at these sort of 1 micron length scales, where you have strong brownmillerite here, perovskite here, but sort of a transition region where you have both the phases present in the material. And we can do this experiment for different thicknesses, different samples. It's so we did this for even as grown LSCO, which should be fully perovskite. Even there, we start to see some pockets, some small pockets, compared to the other 2 samples of brownmillerite. And then the other thing, which I briefly mentioned, you can actually map, you can track your Bragg peak, and you can start to map out the strain in the material. So we can, let's say, for example, sit at any of these locations and do a localized theta to theta scan. So this is how a localized theta to theta scan looks like. So we have the as-grown LSCO, which is the perovskite here, and then the brownmillerite on this side, and then gadolinium half sort of, you start to see the perovskite peak is shifting, and then 3 nanometer shifts even more. And then the brownmillerite itself is not the same lattice parameter for every sample. So the lattice parameter differs widely, and even within one sample, like the blue, it could actually differ. And so using this sort of localized theta to theta maps, we can actually map out the strain of the entire perovskite phase in the sample. Okay, so that's what we did here in this slide, where now we are plotting not just the intensity, but actually the strain in the sample. So this is the out of plane C lattice parameter, varying from 3.806 down to 3.815. And that's sort of a variation of about 0.13 to 0.10%. So that's what we can, sort of the advantage of this technique, we can map out. And we always, interestingly, so we measured quite a bit of filaments. We measured, I think, about 7 or 8 filaments for different samples. And we always see this sort of interesting switch where on the one side of filament, your material has, let's say, positive strain. So this is a line scan taken across this, this line shown here. You have positive strain, and across the filament, it switches to negative. And same for filaments, which are even as long as 50 microns, we sort of see still the same switch. So it's almost as if filaments are growing in the areas where there is a strain gradient, or they're growing to give that strain relief in the material. So we also looked at aluminum 3 nanometer LSCO structure. So another getter layer, and that, whether it's unique to gadolinium or not, so that was one question we had. So we looked at a different layer, and we see sort of the same thing. We see these filaments at almost like 45-degree angle, and we can look at different parts of this filaments. So here, this is this one area, which, and then we can sort of look at a second area where we almost see like 2 different filaments in parallel, and then in the center right here. So it almost looks like you have these, and again, the contrast here, yellow now means brownmillerite, and the dark means perovskite in this case. And it almost looks like you have different brownmillerite regions which got converted, and they always cluster around sort of this 45-degree angle or so. And where we had higher oxygen deficiency, we saw this continuous formation, but where we had low, this is sort of in the initial stages of formation. And that could be because the amount of oxygen vacancies created by aluminum 3 nanometer is slightly different from gadolinium 3. So we sort of missed out on this transition because we got into more homogeneous filaments by that point. And again, so for either of these 2 samples, we saw filaments ranging from 2 to 70 microns, and a total of sort of 7 filaments about 200 in 200 by 200 micron region. And then they were always around 10 degrees or sort of 45 to 60-degree angle. So there was a very specific angle they were at, and they only showed up in 3 nanometer samples. They were never there in the 0.5 nanometer or 1 nanometer sample. So that shows that you require a critical oxygen vacancy in the material to sort of go from one morphology where you have all this random distribution to these organized filaments in the material. And the angle specifically, sort of thinking about that 45 to 60-degree angle for growing of these filaments, we think is related to the fact that the brownmillerite compared to the perovskite unit cell is actually at this 45-degree. So remember earlier I had mentioned that the oxygen ions, the oxygen vacancy order across this 110 channel, so these tetrahedrals are linked along 110 channel, and so the unit cell is actually tilted by 45 degrees. And so that could be the reason why we are seeing, and deviations from these sort of alignments can happen. So in magnetites, for example, people have seen that this brownmillerite phase can actually go through like a cooperative twist to sort of reduce the dipole moment of coming because of these tetrahedrals. And that deviation can easily be from 60 all the way to 70 degrees for these tetrahedral chains. So that could be the reason why we are seeing these specific angles, but slightly deviated because of these cooperative twists happening in this brownmillerite phase. So that part was very interesting. So now in this last 3 months or so, now that we can finally come back to campus and you start working with the clean room, we have been fabricating these electrical devices to actually control these filaments and see if we can apply electrical voltage across the sample and control these filaments. And at that point, we can do a time result study and see how these filaments grow when you apply the voltage across. And that's very interesting because that's very similar to resistance switching memory, where instead of where you use like titanium oxides or to sort of have this filaments grow through from one electrode to the other electrode. So you don't need to transform your entire titanium oxide to titanium 4 oxide 7 to sort of have this resistive switching, you can just transform the filaments, and these filaments could be the ones which are conducting the electrons. In case of LSCO, those filaments would be the one which would actually be conducting oxygen ion. So rather than transforming the entire material from one phase to the other, you can sort of think about a material where you're actually using these inhomogeneities to tailor your devices. So that part is still in process, and we have a beam time coming up in November where we'll be doing this nanodiffraction in a time-resolved manner to sort of image that. So now I'll move on to the second part of my talk, which is talking more about fluctuations and dynamics in complex oxides. I'm happy to take any other questions if there are on the first part. If not, then we'll focus on the second part, which is fluctuation. So moving away from these static responses and sort of capturing fluctuations in materials, or understanding dynamics as materials go through phase transitions. So we talked about that complex oxides have orbital charge ordering or magnetic ordering, and those orderings are typically the reasons which makes these materials interesting. And these orderings, as you go through certain phase transitions, or even if you're far away from phase transitions, we might not be static, they might be actually fluctuating. So for example, magnetic fluctuations in dysprosium spiral have been seen almost like 20 Kelvin before the transition in this material. And similarly, superconducting fluctuations and sort of have been observed in different sort of superconducting systems. And even for orbital ordering and charge density waves in magnetite and chromium, people have seen that down to like 10 Kelvin or even at like 30 or 40 Kelvin, these ordering actually fluctuates. They're not static as we think, and that only change as we get to phase transition temperature. So for example, in magnetite, it goes through metal to insulator transition temperature is around 120 Kelvin. And even way before then, you have these fluctuations which start to happen in these systems. And then as you get to the phase transition, these fluctuations can either get faster or slower, depending upon the mechanism of the transition. So we looked at sort of fluctuations in ferroelectric domains which and ferroelectric domains are different from any of sort of these magnetic domains, which are happening because you have ordering in the electronic structure. In this case, ferroelectric domains occur because you have ordering in the crystal structure. So just a reminder, in case of in a ferroelectric material, are materials which lack an emergent symmetry. So if you have a cubic system that goes through sort of distortions, which results in a tetragonal phase, and the center atom, for example, titanium in this case, would actually shift up or down, will break the inversion symmetry. And as it shifts up or down compared to the other gray oxygens, that would create a permanent dipole, which would give the polarization of a ferroelectric material. And that polarization, as a function of electric field, you can control, and that results in a hysteresis loop, very similar to how you have ferromagnetic material under applied field, where you control the spins. In this case, you control the polarization, which means this titanium atom is shifting from up all the way down. So this is happening because of structural distortions. So for these domains, we're not used to thinking whether they will actually fluctuate. So that's what we're going to talk about in the second half of this talk. And depending upon how you're growing these systems, you can, depending upon the misfit strain of how you're growing this barium titanate thin film, you can have interesting domain configurations. So if you have very low misfit strain around here, you can have A or AB domain structure. So it's a striped domains where your A and B. So you have the titanium atom shifting in A direction, and let's say titanium atom shifting in B direction. So it's A and B refer to the crystallographic directions. So you have this AB sort of striped manner. And as you heat it up, it can actually transform into a different domain structure before becoming the ferroelectric, going back to the cubic phase. And you can control this sort of strain and get different domain structures in this material because the depolarization, the strain in the material can be different, and the depolarization field can be different, and both of these highly affect the domain structure in these materials. So we looked at a specific sort of strain, which was located right around this negative sort of 0.25 value, and where at room temperature we have these AB domains aligned along crystallographic A and B directions, and then as you heat it up, it transforms to AC domains, where now your domains are actually lined in plane A and the C is out of plane. So your domain orientation actually changes. You can still see at 70C, there are still some AB domains actually still present. We looked at these fluctuations, and the way to look at fluctuations in these domain structures is to utilize X-ray photon correlation spectroscopy. So you want to look at domains which are coming because of change in atomic structure. So you need very high sensitivity to the atomic structures, which is given by X-rays. And then we want to look at fluctuations and look at small length scales. So that's something we can use correlation spectroscopy technique to look. And then correlation spectroscopy, especially in like light regime using lasers, has been widely used to study fluctuation in glasses as they go through phase transition or glass transition. But with such small displacements of ions and domain structure, you need to sort of have access to small length scales. So then correlation spectroscopy techniques then have been sort of adapted in X-ray regime, so you can get access to these angstroms, 1 angstrom to sort of 100 angstrom regime, which is where X-rays can look at the material. So this experiment was done at NSLS2, at National Synchrotron Light Source 2 at Coherent hard X-ray beamline. And the key factor here is coherence. So if you have coherent X-rays coming out of the synchrotron, as you diffract from the sample, whichever Bragg peak you are sitting in at, that Bragg peak actually looks a bit what we call as more speckly. If you have any inhomogeneities in the sample, any sort of domain structure, coherent X-rays would scatter through that and would acquire a phase depending upon what sort of inhomogeneities you have in your material. As they acquire a phase, they'll go through constructive and destructive interference within itself. And that destructive and constructive interference would then show up in your Bragg peak, where certain regions are very bright and certain regions are really dark. So these are red areas which are bright and blue areas which are dark. If instead I had incoherent X-rays, which is what we have in our lab source, then you will basically have this interference for each sort of coherent bucket, if you think about it. And then if you average over all, you'll get a very nice homogeneous Gaussian peak, which is what we are used to seeing when we measure our materials. We see a very nice Gaussian Bragg peak, but that loses out all the speckle information. And these speckles are directly a manifestation of what sort of inhomogeneities are present in the sample. And depending upon which Q value we are in reciprocal space, we can actually then track Q-dependent dynamics in the material. So how each length scale is behaving, okay? So, these sort of coherent X-ray scattering gives you very, very valuable information about length scales in your sample, okay? So this is our, the normal Bragg peak right here from the sample. And then because we have an ordered structure, an ordered A and B peak, so because of that ordering, we see a domain scattering peak very close to the Bragg peak. And we can look at this domain scattering peak. You can take a cut across, and that cut looks very, very sort of speckly, and that's coming because of coherent X-rays, which if you didn't, you'd look like a red Gaussian. So if I look at these speckles, which are along this sort of cut, I can then start to map how these speckles are moving as a function of time. So at 55 degrees Celsius, this is, let's say, the line cut across here, and tracking that as a function of time, I can see that the speckles disappear and appear as the time moves on. At 90 degrees Celsius, the speckles are exactly stable. There is nothing happening. The bright speckle stays bright and the dark stays dark. And then again, at 120 degrees Celsius, you start to see these fluctuations. So this is a very nice sort of way to use reciprocal space to look at how my material is changing. In this case, you have no change. So the sample is static. There is no change in domain structure whatsoever. But around 55C and 120C, the sample is changing. So let's look what's going on there. So to quantitatively understand how exactly the sample is changing, what we can do is we can plot an autocorrelation function. So we can collect this image as a function of time, and we can correlate it with itself and then plot that autocorrelation function with itself. And that is directly related to how the intermediate scattering function, which is the dynamic structure factor of the material, evolves. So I can plot the dynamic structure factor as a function of time, and that fit this with an exponential format, a t over tau beta, and can get the tau, which is the critical length time scales of these fluctuations for each temperature. And then beta would be the stretching exponent or the compressed shape, which is what we see in this case. So if you just had exponential dynamics, normal diffusive behavior, beta would be 1. It will just fit an exponential decay as your material is fluctuating. But the fact that beta is greater than 1, that means that the material is actually is jammed in a certain state, and then suddenly as the stresses or whatever is causing that pinning or jamming in that particular state gets released, and the material then fluctuates into a different state and then continues that process. So that gives you sort of faster than the exponential, more of a compressed state. Okay, and that's what we saw for the entire, all the temperatures, and that's looking to be more of a universal behavior of how ferroelectric domains behave. We have done this for orbital domains and magnetic domains and charge ordering domains, and they all seem to behave in sort of a similar manner. So then looking at the time scales, we can then get fluctuation time scales as a function of temperature. And so that's plotted here. We can map out that as a function of temperature. So when we start at room temperature, we still see that these domains are fluctuating. But as we get to the domain transformation temperature, where from AB domains you switch to AC domains, the fluctuations are fastest. And so the time scales drops down. And once the AC domains form, then the fluctuations start to slow down back again. And then at 90 degrees or so at these higher temperatures, they are perfectly stable. And then as you get to the Curie temperature, where even the AC domains are gonna disappear, your material is now gonna transform into cubic phase, the fluctuations get faster in the material. And that sort of correlates with the intensity and the correlation length of this material as well, where if I look at the intensity, which is red data points, as AC domains are appearing, the intensity increases. In the second regime, where most of the things are stable, there are still small fluctuations, the intensity of these domains stay. And then as I get to the Curie temperature, the intensity starts to disappear. However, interestingly, the correlation length doesn't exactly follow the intensity. In this case, it linearly increases. As you have more and more AC domains, you have higher correlation length. But even after the phase transition temperature, the correlation length takes a certain amount of time to get to about this 400 nanometer mark. And that sort of goes back to this AFM, this AFM image, where even at 70 degrees Celsius, you still see some of these other AB domains present. So we think those are the ones which are actually affecting the correlation length. And because those are still present, the system is still not fully transformed into AC domains. You still see these fluctuations in the material, okay? And so we observe faster timescales near domain transformation temperature, and we observe fluctuations all the way up to 25 degrees Celsius, and even at room temperature. So these systems where you are sort of used to thinking that the domains are coming because of this movement of titanium atom, these ferroelectric domains are forming because of that. Even at room temperature, we are seeing the fluctuations in these domains. Now, we're not 100% sure if it's the domain walls which are moving between back and forth, and that's what we are picking up, or if it's actually the domains. So that part, it would be really nice to get some theory feedback. But in such solid state systems, these domains are showing sort of a much more softer nature. So to summarize, I talked about how we can map out inhomogeneities in complex oxides, and how we can measure dynamics and fluctuations in these systems. And this work was done by my grad students. So special thanks to Ian, who worked on the nanodiffraction project, and Jian and Lee, who worked on the ferroelectric materials. And thanks to people who grew these samples. LSCO samples were grown at UC Davis and in collaboration with Yayoi Takamura and Kai Liu. And then the barium titanate samples were grown at University of Groningen in collaboration with Professor Madsen. And then special thanks to all the beamline scientists for making these measurements possible, and to our funding agencies. Thank you all for coming in and listening to our work.
Thanks, Roopali. That was. I have a little bit of an incident here, but thanks. That was really nice. The floor is open for questions now, if anybody has them.
Hopefully I didn't spend too much over the time.
Okay, I have a question. I'm kind of interested in the different behavior of the time scales when you go through the domain transition versus the ferroelectric transition. How do you understand that opposite behavior? Can you think of it as the paraelectric to ferroelectric would be a second order transition where you'd expect critical slowing down, but then something different happens at the domain transition? Maybe it's a first order transition or something like that, or
yeah. So this has been a sort of a point of contention. So the polarization, I mean, the way you sort of the order parameter of transition in these systems is the polarization. And so, or in a bulk barium titanate, polarization changes as a function of temperature in a discontinuous manner. So it's a first order transition. But in a thin film, this transition actually is a second order transition. So, however, this one is sort of, it really depends upon how much strain is this. So in this films, we think that this is actually a first order transformation, this domain transformation transition. And so the difference in behavior could really be coming in because of that. But I mean, a bulk system doesn't show this sort of domain structure, so then it gets harder to compare how that would look compared to an actual paraelectric to ferroelectric transition, which is a first order transition in a bulk system.
May I ask a question?
Sure.
Hi, I'm Jim. What sets these timescales? They seem quite long. In these experiments must take a long time, and that requires a whole lot of stability. I'm very impressed by that. So yeah.
Yeah, I mean, this is a beamline specialized for that, where like they have looked at the stability like you can see, like for 4 hours or so, 3 hours or so, the beamline is really stable. So we really do track that. And then when stuff starts to change, we do see it. So it's, I mean, we spend quite a bit of time characterizing and making sure everything is stable. But that's sort of one of the big things. And to make sure that you're not measuring beamline fluctuations, you're measuring sample fluctuations. So, I mean, because we have done some other samples where we have measured at temperatures of 125 C, where we have also seen flat lines where nothing changes. So from there I can say that these are really stuff in samples. So the beamline is stable for these temperatures. As to how exactly the timescales are slow, and what sort of mechanism is, that's really a good question. And to be honest, I don't have a very good answer for it. Some of the guesses which we have is it could be related to oxygen vacancy motion in these materials, where you have oxygen vacancies moving around, and that could be causing slight changes in this polarization, which we see then in this sort of domain fluctuations. And the activation energy, which we estimated from our fits, is about 0.67, and the activation energy for oxygen ion motion is about like 0.8, 0.9 eV. So similar order. Another sort of theory which has been proposed by another group is that there are some sort of topological defects present in the system which move around. And I'm not sure what they mean by that. And then there is a third theory which is still out. Is it actually the domain walls which are moving? So these are three potential reasons, but we really don't know which of these three is the right answer.
And can I ask just a related question, if you don't mind?
Sure.
Thank you for that. So how small a time scale could you measure?
So the time scale we could measure is actually really dependent on the sample as well. I mean, so two things will sort of define your time scale. One is your detector frame rate, how fast your detector can capture the pattern. So now we have detectors which are down to like 0.1 millisecond or like 0.1 millisecond. So you can get to that. However, once you get to 0.1 millisecond and you measure a peak or you measure like scattering, your sample should be able to give you enough photons to see something, right? So, I mean, usually when you collect data, you average to get some sort of SNR. But if you have a strongly scattering sample, which within 1 millisecond would give you enough photons to sort of do these kinds of analysis, then you can measure those timescales. But like for some of our other samples, like usually if you have some sort of Bragg peak domain, like orbital ordering peak, then you have enough photons to do those kinds of measurements. But for glasses or amorphous systems, you really need to average to like 1 or 2 seconds to even get enough photons to do any kind of analysis. So then it doesn't matter how fast your detector runs, you're limited by the scattering from the sample.
Thank you.
I have a question related to Jim's question, that since the timescales are pretty long, and you even showed real space images of these domains, have people just made videos or investigated them in real space? And if so, how do those timescales agree with your timescales?
So for this particular system, for these particular domains, they haven't done that yet. These phases were sort of stabilized in like 2015, 2019 in these systems. So there's this study out in 2019, which was published in a PRL, where they did imaging using PFM, piezoelectric force microscopy. And there they see that they don't see the timescales, but they just see the distribution of the material. So there's not a real space sort of study out that. And that's related to the fact that how would you image ferroelectric domains, right? So either you use PFM, you use TEM, or you use some sort of X-ray diffraction imaging technique.
Thanks. Sorry, I misunderstood what these images actually were. Thank you.
Oh, I'm glad you asked the question then.
And then another question, you mentioned this exponent, this stretched exponential exponent shows up everywhere.
Right.
Is there a range to the exponent that shows up, or is there some value that they all fall on for some reason?
Right. So typically it's around 1.5. But that I mean, if we were able to capture like the full one, then I would be able to put better error bars on it. But the error sometimes is 1.5 plus minus 0.2 or so. So I don't really want to comment on exactly how it varies, and I don't remember how much was it for the other systems. But from what I remember, it's all for some of these orbital ordering, charge ordering, it has been higher than 1, and somewhere around 1.5.
Yeah. And that indicates glass-like dynamics.
Yeah, it indicates like a glassy dynamics in these systems. Yeah, which is something, in a way, it's fascinating, right? Like these are crystalline systems, but yet the ordering, which is like these sort of superlattice orderings, are acting more like a glassy material.
Yeah, I think what. Oh, sorry. Go ahead.
Sorry, no, I just following up on that. So is A constant across as a function of temperature, and beta as well, or?
Let me see. So let me see if I have A as a function of. Oh, I don't have A. So this is the beta which we measured as a function of temperature. So around, like you can see, around like for most of the temperature, it's 1.5. Where we were really static, where nothing was happening, that's where he fit 1. So I mean, that doesn't mean much. And then this is a point which we are actually measuring again, because we didn't have enough photons at this higher temperature because the intensity was so small. So I don't trust it yet. Yeah. And as in terms of A, I should also put that on my slide. I'm sorry about that. It was constant as a function of temperature. But it is also, but at higher temperatures where the peak starts to disappear, that's when you start to see a decrease in A, because your speckle, A determines speckle contrast, how dark is dark and how light is light. So as your peak starts to get lower in intensity, then the A starts to get lower as well. But for most of the temperature range from like sort of here to here, it was pretty constant. Yeah.
I think what's nice about everything that you've shown today is that, I mean, probably most people know this kind of implicitly, that these interesting oxide systems that all of us condensed matter people like to work on are really messy. But this makes it really explicit that these inhomogeneities are there in time and space.
Yeah.
Yeah.
So I think that's sort of the cool part, that even though we have been doing space for a long time, we haven't been doing time for a long time in these systems. So even in time, they're quite inhomogeneous. Yeah.
Okay, are there any more questions? Maybe from graduate students? Okay, everybody's still shy over Zoom. In any case, thanks, Roopali. That was a really nice talk.
Thank you. Thank you. Thank you for inviting me. This was a fun presentation. Yeah.
Great.